Hello, my name is Tay Netoff, and I'm an assistant professor of biomedical engineering at the University of Minnesota. Today I'm presenting my paper titled The Variance of Phase Resetting Curves with co-authors Bart Ermentrout, Bryce Beverlin, and Todd Troyer. It was printed in the Journal of Computational Neuroscience in 2011. Phase response curves are a simple measure of a cell's dynamics. It measures how synaptic input changes the next spike time of a neuron if it's periodically firing. And it's really useful because you can predict how a network of neurons, if each neuron, when it receives an input, changes its spike time, then you can track all the spike times of the neurons and determine if the neurons are starting to spike together closer over time and synchronizing up, or whether they're actually pushing each other away in time and will not synchronize or synchronize in antiphase. Here is a recording from a neuron. On the top is the voltage trace, and the bottom is the current applied to the neuron through an electrode. And as you can see, the neuron is firing periodically because we're injecting a constant amount of current. Now on the bottom you can see we introduce a synaptic input and at phase phi, and that changes the spike time of the neuron. As you can see, it advances it by delta. Here another stimulus is applied early in the phase, and as you can see, it actually delays the spike. So the phase of the stimulus affects how much change you see in the spike time. In 2005, I published a paper where we measured phase response curves from neurons in the hippocampus and entorhinal cortex. And on the x-axis is the phase of the stimulus, and 0 at the beginning being just after the neuron fired, and at the end of the x-axis is just before the neurons fired again, and the y-axis is how much the neuron changed in its spike time. So about 2/3 of the way through a 150 millisecond period of the neuron, when we stimulated, we got an average of a 20 millisecond phase advance. What was surprising when we did these experiments was that there was quite a bit of noise on the neuron, and at the time phase response curve theory hadn't really addressed the role of noise in synchronization of networks. And so when I ran simulations of network simulations, we made a noise term which attributed how much noise we saw as a function of the phase, and so you can see the error bars accounted for the amount of noise. I fit a very simple function that started off with a constant and then the amplitude of the noise as a function, the square root of the time prior to the stimulus. And this did a reasonable job of fitting the variance, as you can see here. Unfortunately, it was an ad hoc measure, and there was no real justification for why I used that function. And Bart Ermentrout approached me and said that he didn't think that the function that I created was correct, but that he would think about coming up with a better solution. And this paper is about how we fit that noise function and showed that his more principled way of deriving the phase variance as a function of the PRC actually does a better job than this ad hoc measure that I had developed. Generally, we just substitute the time since the last spike for the phase of the neuron, and that works generally pretty well. The moment the neuron spikes, we know exactly what the phase is. It's 0 at that time. And then over time, we don't really know what the phase is until the neuron spikes again, and then we can exactly determine the phase. So as noise comes in, there's an increasing ambiguity in the phase. And so here we're representing on the x-axis the phase of the neuron, and it becomes a Gaussian distribution. And then the moment we stimulate the neuron here at 0.8, that Gaussian distribution goes up to the phase response curve, and we map it through to the phase on the next cycle. And normally we just map through the phase of the stimulus, but because the phase is actually unknown, we map through the entire distribution. And if the slope of the phase response curve is less than 1, then that distribution becomes tighter after the stimulus. And if it's greater than 1, it actually becomes wider. The variance then continues to grow until the neuron actually spikes. This is equation 7, which is the main finding of the paper. Theta of t is the variance at phase or time t of the stimulus. Beta is the stimulus amplitude. Delta is the phase response curve, and delta prime is the slope of the phase response curve. And c is the amplitude of the noise term. And in this, you can see we integrate up to the time of the stimulus, and then and calculate the total power of the phase response curve up to that time, which determines the variance due to the noise drive into the cell. And then from the time of the stimulus to the end of the phase, we calculate, we continue integrating up the remainder of the variance after mapping it through. In this figure, Bard took some canonical model neurons and calculated the phase response curve and the variance of the phase response curve directly from the model, and then where he uses the phase response curve as a sine function in the left column and 1 minus a cosine function in the right column, and then shows that the variance calculated as a function of the phase is actually quite well predicted from the model in the solid line compared to the dots, which are measured numerically from simulations. Likewise, he took a Hodgkin-Huxley model and measured the phase response curve of the neuron while driving it with noise, and showed that the variance is also pretty well predicted according to that equation. In this figure, we took the variance that we measured from the phase response curve directly from the neuron using my ad hoc measurement. So in the right-hand side, the variance as a function of phase is labeled as experimental. And then the theory based upon the measured phase response curve and the expected variance. And you can see they're quite close and well correlated. Here's another example where we measure the phase response curve's variance using both the ad hoc and Bard's method, and found that the variance looks pretty similar, but the variance actually looks a bit better from the new method, in that the variance actually decreases towards the end of the phase a little bit more. We went through our entire database of experimentally measured phase response curve and found on average the new method did a much better job of measuring the phase variance than the old method. To test if this model made any real significant differences in simulations, we took networks of neurons where we modeled them using the phase response curves, updating their spike times every time a presynaptic neuron fired. And we kept the PRC with the shape noise versus PRCs with flat noise and a full conductance model, and found that including the phase variance gave us much more accurate predictions of how well network synchronized than sort of ignoring the noise and leaving it flat throughout the phase. Finally, I just want to show some movies of how the phase-dependent variance changes as a function of the noise amplitude and the stimulus amplitude. So here is a map. On the x-axis is the distribution of the neurons' phases. It's a probability distribution. We start off with a delta function just before the stimulus, and then we map it up to this sort of light blue line in the center, and then you can see the distribution after the stimulus. So it looks like a Gaussian distribution. We can then keep remapping this through and make a movie over several iterations. You can see the iteration number there and see how the distribution evolves from stimulus to stimulus to stimulus. So with each stimulus, you can see the Gaussian gets wider and then approaches the in-phase solution. As we increase the noise, you can see the steady-state solution is more distributed in phase. Playing again, you can see it converge, and it will converge to a steady-state solution, which can be calculated from this eigenvector with the largest eigenvalue. Here we plot the variance as a function of phase and the steady-state distribution as we change the stimulus amplitude, epsilon. Finally, we vary the stimulus amplitude and show the phase-dependent variance and the steady-state distribution as it varies. We'd like to thank you for watching this video and thank NSF for support for Bart Ermentrout and myself, and grant an aid from the University of Minnesota for supporting Bryce Beverland. You can, of course, contact me at tnetoff@umn.edu or go to my website if you have any questions. Thank you. Bye-bye.